Friends, very good morning to everyone. Last classes or last presentations, we have dealt with the retrosynthetic strategies utilized for synthesis of three-membered ring system and six-membered ring system. Today's subject of discussion is retrosynthetic strategies for four-membered ring synthesis. Though five-membered and six-membered ring systems are most widely used ring system, but four-membered ring systems are used rarely as the drug molecules. But still, this plays a very important role in heterocyclic chemistry and carbocyclic chemistry. That's why these are also having importance. Hence, this discussion is. The first and foremost approach for synthesizing four-membered ring system is cyclization. If I have a four-membered ring system with an heteroatom, I'll break upon the molecule over here adjacent to the heteroatom. This general strategy what we follow in CX bond disconnection approach, the same strategy can be followed here. If I break upon the CX bond, the heteroatom gets electron richness. It acts as a point of donor synthon, and the one which has the adjacent carbon will get the positive center, and that act as a acceptor synthon point. If I add a leaving group on the acceptor synthon point and I take this kind of molecule and heat it, I can cyclize. Here, this involves cyclization via carbon heteroatom bond formation. The bond can be formed between the electron deficient carbon and the heteroatom to synthesize four-membered ring system. I'll take a molecule which has a carbon and a heteroatom with electron richness and a leaving group to attach it to the third carbon, so that this leaving group is also an electron withdrawing group, which renders this carbon positive. When I heat it, the excess electrons on the heteroatom attacks on the positive center, and the leaving group Lg as I represented, it leaves and cyclization occurs, and it gives rise to a four-membered ring system. The same cyclization can be effected by formation of carbon-carbon bond. That is cyclization via carbon-carbon bond formation. In this case, we take a molecule to which there is a heteroatom and to which there is an alkyl group attached. Because of this electron withdrawing group and heteroatom, it renders this carbon adjacent to this heteroatom acidic enough to lose the proton. In a street with a strong base, it takes the proton, giving rise to a carbon ion. It is an electron rich center, and the carbon which is attached to an electron withdrawing leaving group is electron deficient center, and when we heat it, the cyclization can occur. The excess electrons on the carbon ion is donated to the carbocation, and this carbocation has to maintain its tetravalency. Hence, the leaving group leaves away with its electron pair, and cyclization occurs to give rise to a four-membered ring system. This is the general approach followed. Another approach which we follow for four-membered ring system synthesis is cycloaddition reaction. We have seen 4 plus 2 cycloaddition reaction, that is Diels-Alder condensation or Diels-Alder cycloaddition, to give 6-membered ring system. The same strategy is utilized here to prepare 4-membered ring system too. Here I have a molecule with 4-membered ring. I break upon like this. This part will become one synthon and this part will become another synthon. And I'll get two alkenes. These two alkenes, this has 2 pi electrons, this also has 2 pi electrons. 2 pi electrons of this and 2 pi electrons of this add to each other, addition takes place, and cycloaddition, that is 2 plus 2 cycloaddition takes place. As we know, this is an electrocyclic reaction in which there is no intermediate form. Here the electrons move cyclically, that's why they are electrocyclic reaction. It undergo 2 plus 2 cycloaddition to give rise to a 4-membered ring system. In case of 6-membered ring system, we carried out 4 plus 2 cycloaddition reaction to get the target molecule. Here we follow 2 plus 2 cycloaddition. Out of this cyclization and cycloaddition, which is more amenable? Definitely it is cycloaddition. It is more amenable for the synthesis rather than cyclization of the open chain ring system. One more approach is followed. Before that, I'll give an example for cycloaddition reaction. I'll take RCX and R2C double bond CR3. This has 2 pi electrons and this has 2 pi electrons. This can shift the electrons cyclically and gives cycloadduct, that is 4-membered ring system. Another approach which we follow is ring expansion. I'll take a 3-membered ring system like this. A 3-membered ring system with sulfur atom. And because of the sulfur atom present in it, it is electronegative in nature. It pulls the electrons, renders the adjacent carbon acidic enough to lose the proton. And I treat with a trimethyl sulfoxide in the presence of a strong base like sodium hydride, Na plus H minus. This can abstract a proton from dimethyl sulfoxide. This proton leaves the electrons on the carbon, giving rise to carbanion. As it is electron rich, it is unstable. To regain its stability, that excess electrons, it donates to the electron deficient center in the 3-membered ring system with sulfur. The carbon here has to maintain its tetravalency for its stability. That's why the bond between the carbon and sulfur breaks and that excess electrons are moved on to the sulfur. It gives rise to a open chain system. Now I heat it. The carbon adjacent to this dimethyl sulfoxide group is positive because of the electronegativity of this sulfoxide group, which renders this carbon positive center. This excess electrons on sulfur is given to this electron deficient carbon, and as this is a easy leaving group, it loses this group dimethyl sulfoxide. and it gives rise to a cyclized ring system. A three-membered ring system has got expanded, enlarged to give a four-membered ring system. This is the strategy which we follow for four-membered ring synthesis. Other than this cyclization and cycloaddition. One more example I can give you over here. The ring contraction. I take five-membered ring system and I treat with a base. The five-membered ring system is pyrazolone, 1 tosyl, 3 bromo, 2 pyrazolone. I treat with a strong base like sodium methoxide. The carbonyl carbon is the positive center as it is flanked between the nitrogen and electron withdrawing group and the oxygen. Sodium plus and methoxide minus. This is electron rich and this is deficient. Unlike poles attract each other. Once it attacks, the bond between the carbon and nitrogen breaks and ring opening occurs with the addition of OMe group. Now, the nitrogen here has lone pair of electrons and these excess electrons are donated to the electron deficient center. This is electron deficient as it is flanked between two electron withdrawing group bromine and carbonyl. Once it attacks on this carbon, it has to maintain tetravalency. Bromide gets kicked off and I'll get cyclized. I have taken the five-membered ring system and contracted to four-membered ring system. This is another strategy which we follow for four-membered ring synthesis. One more example I will give for ring expansion. There in the first example I have given an heterocyclic three-membered ring system. Here I am giving an example of carbocyclic three-membered ring system. This carbocyclic ring system is attached to an heteroatom like sulfur because of its electron withdrawing ability. This is acidic enough to lose the proton. That's why I treat with N-butyl lithium, a strong base, which abstract the proton from the carbon which is adjacent to the heteroatom, giving rise to electron rich carbon, that is carbon ion. And then this carbon ion compound I treat with an ketone. The ketonic carbonyl carbon is positive center and this electron rich center, and I heat it. This attacks on the positive center and the pi electrons moves onto the oxygen. O minus is unstable. Adjacent to it there is the positive center sulfur. That excess electrons are donated to it. The bond is formed between oxygen and carbon and this gets kicked off. When I heat it with an acid, it gives a four-membered ring system. A three-membered carbocyclic ring system I converted into four-membered carbocyclic ring system. This is the strategy followed for four-membered ring system. Summarizing, four strategies are followed: cyclization, cycloaddition, ring expansion, and ring contraction. Whether it is a carbocyclic ring system or an heterocyclic ring system. Next presentation, I'll be giving the retrosynthetic strategies for five-membered ring system. Till then, have a nice day. Thank you.